Hello, can you hear me? Hello, I am
Yes,
audible.
ma'am. Yes, ma'am. Yes, ma'am.
Yes, ma'am.
So we have just started discussing the induction motor. So what so far we have discussed is that how the three-phase voltage is generated by basic principle, and then we have seen what is the nature of the MMF, which is where MMF when the three-phase current winding is carrying current, because that is important, because the for induction motor operation we are discussing three-phase induction motor now. So the generation of rotating magnetic field is absolutely necessary. So what we have in an induction motor is on the stator we will have slots. In the slots we will have distributed three-phase winding. So induction motor, remember that it is a singly fed motor. That is, in case of DC motor, it is a doubly fed, in the sense that both the armature winding and the field winding has to be supplied. Whether it is from a separate supply or whether shunt or series connection, that is immaterial, but has to be supplied separately. But for induction motor, what we have on the stator, we have a regular three-phase winding. So this winding is connected to the three-phase supply. So this is the only point of electrical power feed. So the electrical power is fed to the stator winding. So this stator winding, while carrying current, it is a balanced winding, so it will carry a balanced three-phase current. So as we have discussed earlier, that balanced polyphase winding carrying balanced current will create a rotating magnetic field. So this three-phase winding will create a rotating magnetic field. Now, the speed of the rotating magnetic field depends on the number of poles and the supply frequency. It is given by 120 F by P, where P is the number of poles. This is in RPM. Direction of the rotating magnetic field can be changed if we just interchange two of the supplies, so that the sequence is changed. Supply sequence, if it is changed, the direction of rotation will change. Now, as the stator field creates a rotating magnetic field, what we have on the rotor, to the rotor we do not give any direct electrical supply. The rotor gets the power from the stator by the principle of induction. So on the rotor we have a short circuited winding. Basically we can have two type of winding. One possibility is that we can have a regular three-phase winding on the rotor, which is connected to slip rings, 3 slip rings, and externally through brushes the winding can be shorted. Or we can have a cage winding. Cage winding means on the rotor slots we have bars. Normally all motors normally available are aluminum, might be a copper also. High efficiency motor will have a copper cage, and the cage is and the bars are shorted by two end rings on both sides, so it is a short circuited on itself. So basically we can have two types of, depending on type of rotor, we can have two type of induction motor. That is slip ring induction motor. It is also called the wound rotor induction motor, externally shorted through slip rings, and the squirrel cage induction motor shorted on itself. Now, when we go for the advantage and disadvantage of these two motors, we will see both have some advantage and disadvantages. The slip ring motor, just without details, I can tell that the slip ring motors, the number of poles, the stator, if it is wound for say 4 number of poles, the rotor winding should also be wound for 4 number of poles. The same number of poles the rotor and stator should be wound for. For squirrel cage motor, we have bar winding, so it adapts itself to the number of poles of the stator. So from the point of view of speed control, the squirrel cage motor has certain advantages. If the stator winding is such that it can be rewound for more than one number of poles, then the same motor can be used as a pole changing motor, and as the number of pole changes, so synchronous speed changes, so there will be a change in speed. Speed control is possible. Another advantage of squirrel cage motor is that there is no moving contact. Only power is given from the supply to a static winding, so it is fixed contact, no moving contact, so no wear and tear. So squirrel cage motor requires very little maintenance. However, these bars which is placed on the rotor are shorted on both the side by end rings, and these joints between the end ring and the bars, that is difficult to make because these joint we want to be the resistance to be minimal. So it is difficult to make, and the very common fault of squirrel cage motor is a broken bar. That joint gets disconnected. Whereas for the slip ring motor, as I have told, we cannot have a pole changing motor because both the stator and rotor should have the same number of poles. But and it has a moving contact, the slip ring and brush. So the moving contact means it requires certain regular maintenance because there will be wear and tear wherever there is a moving contact, and obviously there is a possibility of sparking. But the advantage or main advantage of squirrel cage motor is that without directly shorting the winding, we can insert external resistance. And when we go for the characteristic, we will see if we can insert external resistance as starting, then we can have a high starting torque. So squirrel cage motors are advantageous when the load which the motor is driving is a high inertia load, so that at starting it requires a large torque. So this is the basic. Now what happens? This is the basic drawing of an induction motor. So the stator winding has created rotating magnetic field. As per my figure, it is rotating in the anti-clockwise direction, and for a particular instance, say this is the stator magnetic field axis, north and south. So if this is the position of north and south for this instant, then the EMF induced in conductor A, say at here, and A dashed here will be maximum, as we have discussed earlier, and the EMF in conductor here, B dashed and B here, will be minimum or 90 degree, that means it will be 0. The figure might not be exact because it is drawn by me on paint. So anyway, so these two conductors will have maximum EMF, and this B and B dashed will have at 90 degree, which are at 90 degree, will have minimum induced EMF or 0 EMF. Now, in between other conductors will have induced EMF depending on their flux linkage, and that depends on the angle, the cosine of the angle between this conductor and the flux axis, as we have discussed while deriving the winding factors. Now, this conductor A does lie at the maximum, is linking the maximum flux, and it is carrying a large current also, so it will create a torque. Similarly, these conductors also will create a torque, and you can find that this is a now. Before we were going that, for simplicity, let us consider that the winding has negligible inductance, so this is basically resistive. So the EMF what we have shown, the current is also in phase with it. So this conductor, if it is mainly resistive, then this conductor will have a maximum current, this will have a maximum negative current, and this is lying under north pole, this is lying under south pole. So you can find this current and flux interact to produce a torque. You can get the direction from the Fleming's rule, and you can see that both this conductor experiences a torque, and the torques are basically in the same direction. In the same way, all these conductors will experience a torque. The magnitude, however, depends on the magnitude of the current carried by the conductor and the flux it is linked. But the direction remains the unidirectional. So all the conductors experiences a torque, and so the rotor will rotate. So basically, the same whatever we have explained earlier. That is why this always, according to Lenz's law, the effect opposes the cause. So what is the effect? The effect is the induced EMF. Due to that, this current is flowing. And what is the cause? Cause is the speed difference between the rotating magnetic field and the static rotor. So the effect is that the rotor will start rotating in the direction of the rotating magnetic field. Ideally, the rotor will try to catch up with the synchronous speed. It will try to reach the synchronous speed. However, it can never, in practice, it can never attain the synchronous speed, because at synchronous speed, what will happen? If both the rotating magnetic field and the rotor is rotating at synchronous speed, the relative speed difference is 0. So basically, rotating magnetic field is a magnitude is constant. So you can see that the conductor flux linkage will no longer change with time. So there will be no EMF induced. So there will be no current flowing. So there will be no torque produced. So basically, the rotor will attain a speed slightly less than the synchronous speed, so that the torque developed is just optimum to drive the rotor. For initially, let us consider it is a no-load motor. So if there is no load on the shaft, then basically the motor only has to overcome the mechanical losses and the losses encountered in that eddy current and hysteresis loss. So the speed difference between the synchronous speed and no-load speed is very small. Basically, for very large motors which have roller or ball bearings, the mechanical loss percentage is very small compared to the rating. So the speed, no-load speed, is almost equal to the synchronous speed, very slightly less than the synchronous speed. Now, what happens if we put load on the shaft? If we put load on the shaft, then the power requirement increases. So the motor speed will decrease slightly. So in the steady state, the motor will run at a speed slightly less than the synchronous speed, such that the power developed will be sufficient to overcome the losses and to drive the load. Now, here we define now what happens as the load increases, so the rotor speed will decrease. Now initially, what we were discussing, that initially when the rotor was at rest, the rotating magnetic field created by the stator was rotating with respect to the rotor at synchronous speed, that is corresponding to the supply frequency. So the electrical quantities, the induced EMF and the current, has the frequency as the equal to the supply frequency. Now what happens when the rotor starts rotating? When the rotor starts rotating and it has attained the steady speed at no load, then the speed difference between the rotating magnetic field and the rotor is rotating magnetic field and the rotor is very small. So the relative speed between the rotating magnetic field and rotor is the difference between the rotating synchronous speed and the rotor speed. So the frequency of the electrical quantity, that is the EMF and the current, that will be proportional to the relative speed. So that as the speed difference decreases, that frequency also will decrease. So the FA and so as the motor speeds up, what will happen to effect? That is, the first effect is that the initially what is the EMF induced in the quantity rotor, the induced EMF will be say E. That will it is basically due to induction. So it will, if you remember the transformer equation, it will be 4.44 pi F pi M into here. Instead of T2, there will be that effective number of turns. But as the rotor speed increases, so the frequency will decrease. So frequency decrease means in the rotor EMF equation, the F will be now reduced. Now, what will be the magnitude of F? We define a quantity slip. What is the slip? Slip is the, if ns is the rotational speed of the ns is the synchronous speed, n is the speed of the rotor, then ns minus n is the relative speed of the rotor with respect to the rotating magnetic field divided by ns, or the synchronous speed, is defined as the slip. So this can be written as this n, if we multiply it by p, so p ns minus n by ps. So this will also be equal to f minus fr by f, where f is the supply frequency, fr is the rotation frequency corresponding to the rotor speed. This is equal to f2 by f. So f2 is the frequency of the rotor quantities. So what is the effect as the speed increases? So that the speed increases, the magnitude of the EMF induced in the rotor conductor will decrease, and also the frequency of the electrical quantities in the rotor, that also decreases. Now, as we have defined slip from here, you can see that the rotor speed is given by ns into 1 minus s, where s is the slip. It is called slip. So as if it is visualized like that, the rotor is trying to catch the synchronous speed, but it cannot, and it slips back. So it is that's why the difference in speed is known as slip, where f is the supply frequency, and so this is the f2 is the frequency of the rotor quantities. Now, under no load condition, as I have told, that the only thing the motor has to overcome is that the motor loss, mechanical loss, motor losses, and that current is small, so motor I square loss is small, so mechanical losses, and additionally what will be there, the iron losses. So that portion, so the power which is developed by the rotor circuit will be sufficient to overcome these losses only. So that requires a very small slip. So the no load speed is almost equal to the synchronous speed. Now, when we put load on the shaft, so the power requirement increases, so the rotor slows down. As the rotor slows down, that means n will decrease, so your slip will increase. So your slip will increase. So as we load the machine, the slip will speed will drop and the slip will increase. Now at no load, the slip is generally very small. Say that normally slip is expressed as percentage or a number, because you can see this is a ratio. So this is a pure number. No load slip is around 0.01, might be less than that. In large machines where we use ball or roller bearing, the percentage is still might be still smaller. But as we load the machine, the slip will increase. Well-designed induction motor for full load normally have a slip in the range of 4 to 5%. Now, what I have discussed here, I have considered that the rotor conductors have negligible inductance, but that assumptions we made are not very practicable because we have lots of amount of iron. Both the rotor core and the stator core are made up of iron. Basically, windings are embedded in iron, so the rotor winding should have some inductance, considerable inductance it has. So what I have shown. এক মিনিট, হ্যাঁ, এই ঘর হয়ে গেছে, নিচের বারান্দায় কর দিয়ে যা। So as I have shown here, the current is maximum in the conductor, which has maximum induced EMF. That assumption does not hold good. Actually, as a rotor conductor has considerable inductance, so current will basically lag the induced EMF. So basically, current will be maximum not in A dash, but in some conductors, say here, which is lagging behind the conductor which has a maximum EMF. That is, this figure will still represent the EMF induced in the conductor, but the current distribution will be different. That is, current will be maximum in these two conductors and zero in somewhere here. So in between there will be the distributed accordingly. So basically, what is the effect? You can see that still the torque is developed. That is the due to the current and the rotating flux interaction of these two. A torque is developed, and the direction of the torque also remains the same. But the effect is that basically the magnitude of torque will decrease because the here the maximum flux and the maximum current where is interacting here. However, where flux is maximum, current is something different. So there is a lag angle. And besides that, the current magnitude itself will decrease because the current is basically the induced EMF divided by the total impedance. So we have initially neglected the reactance. So if we add the consider the reactance, so magnitude of current will decrease. So basically, if we consider the reactance, the torque, actual torque developed will decrease due to two reasons. The impedance increases and the current therefore reduces, so the torque magnitude reduces, and the phase angle is introduced between the rotor current and the air gap flux. So the resultant torque decreases. So the effect of the reactance is that it reduces the torque developed. But however, we have seen that the motor speeds up, so the frequency decreases. So inductance, we know it is dependent on the frequency. So as frequency decreases, so effect of inductance will become less and less important. So if we consider that the secondary winding, the rotor winding has an inductance of x2 at standstill, that is x2 is the inductance corresponding to the supply frequency. But when it is moving at a speed such that the slip is S, then its secondary frequency is SF. That F2, as we have defined earlier, that is this F2 will be SF. So basically the inductance will be now SX2. So this S, we have seen that it is very small. So the inductance is negligible when the motor is running with its steady speed. So at no load, the speed is very near to the synchronous speed. So inductance will be insignificant, say 0.01, x2 into 0.01 at no load steady state speed. The current depends on the value of the rotor resistance and so current becomes for steady state condition. The rotor current basically depends on the rotor resistance. So lower is the value of the rotor resistance, higher will be the current value. So higher will be the torque produced, so bringing the speed more near to the synchronous speed. So from the view of starting, when we require a large starting torque, so that the high ratio of resistance to reactance is desirable. But however, if for running condition we have a high resistance, that means the I square loss also will be high. So from the efficiency point of view, high resistance is not advisable. So we require a high resistance during starting so that we can have a high starting torque. But from the efficiency point of view, the resistance should be low so that I square R loss is less. So the two conflicting requirement is there. So as I have told initially that one advantage of slip ring motor is that we can add external resistance as starting so that initially we can have a high resistance in the rotor circuit and we can have a high starting torque. But when the motor has attained the speed, we can cut off the external resistance. So motor can run with a low resistance as the rotor winding is designed for. In case of squirrel cage motor also some variation of resistance is obtainable by design when we go for the motor construction. Then we have some deep bar rotors, double cage rotor construction, so that initially we will have a high effective resistance. Because initially the advantage is taken, the main principle behind that deep bar rotor or double cage rotor is that initially the frequency is high. So frequency is high means inductors will be high. So basically the rotor conductors will have high inductance. So it will have uneven current distribution. Current will try to flow through the surface only. So effective resistance will be increased. But when the frequency becomes very low, so the current distribution becomes even. So the effective resistance will decrease. That's how we can have a high starting torque for the squirrel cage motor also. Now high ratio, as we have discussed, the high ratio of resistance to reactance is desirable for starting. However, resistance should be low for running because that efficiency will be high. The induction motor at no load runs at a speed very near to the synchronous speed. Thus, the slip S is very small. Consequently, the induced EMF is SE2 is also very small. Now, as we load the machine, as I've told that the machine speed will decrease. So similarly, the slip will increase. So SE2 will increase. So that will increase the current flowing in the rotor circuit also. So the power which is transferred, power is basically transferred inductively from stator to rotor. That also is increased. So induction motors are called generalized transformer. That is, the rotor of an induction motor has no electric, that is, in case of transformer, what we have two windings, the primary winding and the stator secondary winding, which are electrically isolated, only connected by magnetically connected by the mutual flux. Similarly, in the induction motor, the rotor is not electrically connected to the supply or the stator. but it gets power from the stator by the process of induction. That is, the power is transferred from the stator to the rotor by process of induction through the air gap, and this electrical power is converted to mechanical power, and it drives the load in turn. Now, for this reason, now one thing you can say, in case of transformer, the primary and secondary side, the frequency of the quantities are also same. Now, in case of induction motor, you can note that the physical frequency of the stator circuit and rotor circuit are different depending on the speed of the rotor. So it also transform the frequency also. So it is called the generalized transformer because it transfer all possible quantities, that is voltage, current, frequency, and then is transferred can be transformed from stator to rotor side. Now, as I have told that we can have two type of rotor, basically the cage rotor and the slip ring rotor. Now, cage rotor, it consists of series of conducting bars. These bars are conducting bars which are placed in the rotor slots, and on both sides it is short circuited by a short circuiting ring. So what happens, depending on the position of the stator pole, that EMF is induced in these rotor bars, and this number that it will create turns like this. Say this is a pole pitch, then the current this will make a turn. Similarly, this will also make another turn. Then for this next pole, this will be a turn and this will be another turn. So you can this consists of a series of conducting bars accommodated in rotor slot. The bars are shortened by conducting rings. So this shows the rings. This is a developed view. That is, we have cut the squirrel cage and expanded the winding. So it may be considered as a series of full pitch turns formed by pairs of bars, one pole pitch apart, joined at its end by the closed loop by the end winding. That is, this can be one turn, this can be one turn for a particular pole. For this one, this can be one turn, this can be one turn. So this way we can have, and now that is what happens if the number of poles connection of the stator winding changes. So this pole pitch will change. So the current distribution automatically will adjust itself. So the number of poles of the rotor bar, rotor winding also will change. So rotor 12 gauge rotor can be used for pole changing motor. So from here you can see that the end winding carries the summation of the currents. That is, this end winding is this one. So this has a summation of the current. The current between this bar and this bar. So this is the summation of the current going in the bars. Further, in an actual case, there may not be a whole number of, that is here what I have shown here, that is there are certain rules for the number of stator and rotor slot combinations, where we will discuss when we go for the construction of the motor. So the number of rotor slots might not be integral. That is, per pole, rotor slot per pole might not be integral. So, however, the rotor current distribution will adjust itself according to the pole pitch. However, we will discuss the motor operation considering a full pitch coil. it hardly affects the calculation what we will discuss afterward. So this can be the current. You can show that from here. What is the current? If this bar, if this is the current for this bar, you can see it is double more. This plus this. So it is this current for this turn, for this turn. So this is more. Again, this is the same value. Here also this current and this current will be same, considering the impedances are same. This value and this value are the same, but in the negative direction. So if we plot this current in the bars will have approximately a sinusoidal like distribution, current distribution like this, and the current in the rings will be summation of these currents. So current in the ring will be maximum here, and this will be minimum here. It is divided in both directions, so minimum here. So this way, this current distribution in the ring is approximately like this. Now when we are we will derive the expression for the performance quantities. We consider that the current distribution in the rotor, bar rotor, is approximately sinusoid. So it creates a sinusoidal current shift. The assumptions of the rotor current distribution is justified for the reason that only the fundamental, actually this might not be a sinusoid. The wave might be something slightly different, but we consider the sinusoidal distribution because the reasons are that the fundamental sine component is the component which contributes to the normal torque. It will have some harmonics, but that does not affect the motor, add to the torque produced by the motor. And the harmonics in most cases are small, contribute only some secondary effect. So we will consider the sinusoidal current sheet distribution in the cage rotor. Now for the slip ring rotor, what we will have in the rotor is the regular three-phase winding. So you can visualize that the three-phase windings, the sides lie in different slots. So the flux linkages are different, but however, the current cannot be different. Here in the bar winding, physically the current values in different bars can be different, but not for the slip ring winding, which is a continuous winding. So that particular winding of A phase winding always carry the same current, B phase current, and C phase current. So current is the carried by the conductors at the same. Now the slip rings are shorted externally. The conductors of one phase carry the same current, and the current distribution is thus different from whatever we have shown for the cage rotor. Now we have seen that armature reaction of a uniformly, now we have derived the armature reaction of a uniformly distributed winding in the previous class, and we have seen that the distribution of the armature MMF, that is trapezoidal in nature, and the trapezoidal MMF, we know that it can be break up into a fundamental and some harmonics, odd harmonics, because if a wave with half wave symmetry does not have that say even harmonics, so it will have certain odd harmonics, and the so as fundamental is quite large in magnitude and fundamental is predominant. So in practice for that slip ring motor also, for normal calculation, unless we go for a very precise calculation, we will consider the distribution to be sinusoidal. The cage and slip ring rotors are thus from electrical point of view equivalent as long as attention is confined to the fundamental sine wave only. That is for the cage winding. We can consider it the current. It creates a current which creates a sinusoidal current sheet. Similarly, neglecting the harmonics, the sleeping motors also creates the sinusoidal current state distribution. 1 minute. Hello. হ্যাঁ গেছিলাম পরে বলছি আমি ক্লাস নিচ্ছি so the cage winding is so the choice between the two windings is based on most cases as following. As I have told that the cage winding is permanently closed, so its electrical characteristics are fixed. We cannot change its resistance and reactance and in case of cage winding. Whereas for slip ring motors, it permits variation of electrical characteristic by insertion of resistance in the rotor circuit. So we can have a high starting torque by inserting resistance during starting and then removing the resistance after the motor has speed up. And for the cage winding, is adaptable, as I have told, it is adaptable to any number of poles, whereas slip ring is wound for a particular number of pole P. So the speed can be controlled by reconnecting the stator winding if the winding is designed in such a way, and we can have a pole changing motor if we have a squirrel cage variety. And another advantage of squirrel, as I have pointed out, that it does not have a moving contact, that is slip ring and brush assembly, as in case of slip ring motor. So it requires very less maintenance. It is very rugged. Squirrel cage motor is one of the most rugged electrical motor available. So now to develop the induction motor theory, it can be developed into one easiest way is to the simple theory of the induction motor depending on the constant flux. As I have explained that the stator winding, as it is a three-phase winding, it and fed from a three-phase supply which will create a rotating magnetic field with a constant magnitude. That is, the maximum value is constant, but however, at any particular instant, that flux is distributed sinusoidally across the air gap, but that sine wave is rotating, that is moving across the air gap at synchronous speed. Now, these constant, this constant, only a part of this flux is mutual, as in this is case of transformer. We have seen that the flux which is created by the primary, a part is the mutual and there will be some leakage flux. In case of transformer, the core were both the windings were wound on an iron core, so that leakage flux was very small. But here, basically, if we compare, the stator is the primary and rotor is the secondary, and in between we have an air gap, so which has a considerable reluctance to the flux path. So basically, the flux which is created by the stator winding, a part of this is mutual, which links both the stator and the rotor, and remainder is the leakage flux. And this percentage of leakage flux in case of the induction motor will be considerably larger compared to the transformer because of the presence of air gap between the stator and the rotor. The leakage flux is proportional to the, and as in case of transformer, we have seen that the mutual flux remains constant from no load to full load, but the leakage flux were proportional to the load current. This is true for induction motor also. The new mutual flux must, but the leakage flux is proportional to the current. So as we increase the load, the leakage flux increases, but the flux which is created by the stator, that is constant. So what is the mutual flux is the flux created by the stator minus the leakage flux. So if the leakage flux increases, that means which load actually the mutual flux decreases. It cannot be assumed constant as in case of transformer. But however, the change is very small, and for our normal operation, for deriving the normal operating normal equations of the motor, we will consider this flux to be constant. The resultant mutual flux consists of a rotating field, and it is now to derive the expression, we have these things, that is P is a number of pole pair, F is the supply frequency, F2 is the frequency of the rotor, EMFs and current, Fr is the rotational frequency, that is N into P, where N is the rotor speed, Ns is the synchronous speed, N is the rotor speed, E1 is the stator induced EMF per phase, E2 is the rotor induced EMF per phase, T1 rotor turns per phase, obviously the effective turn, and T2 is the rotor turns per phase, S is the slip, Fn is the mutual rotating flux in Weber. We define these quantities, that is slip is defined as we have defined earlier, that is slip is Ns minus N by Ns, that is F2 by F. Rotor speed, so is N is equal to Ns into 1 minus S in RPS and 60 F 1 minus S by P in RPM. Under no load condition, slip is negligible, full load is a small percentage, and normally it will be well-designed motors will have maximum slip around up to that 4 to 5%, not more than that. Now, EMF induced in the stator winding, E1 will be given by 4.44 kW1 F T1 pi m, where kW1 is the winding factor of the stator, fundamental winding factor. T1 is the number of turns, and the rotor phases F2 is SF. So E2 is 4.44 kW2 F2 T2 phi m, where kW2 is the winding factor of rotor winding, and in place of F2, if we put SF, then it will be 4.44 kW2 SF T2 phi m. Now E2 dashed we can define as, this is equivalent rotor. This is as in case of transformer, it is here also to we will develop a equivalent circuit. So it is convenient to replace the actual rotor by equivalent rotor having the same number of turns as per phase, disposed in the same way. So if we that in case of transformer, we have defined E2 dashed as N1 by N2 into E1. Here also we defined as kW1 T1 by kW2 T2 into E1 this way. So that E2 dashed is equal to E1. At standstill, the rotating field this equation, some typing mistake is there. I will correct when I will send it to you. Now, at standstill, the rotor field has the same speed relative to both the stator and the rotor. So E2 dashed is equal to E1. But at slip S, E2 dash falls to S E2 dash. So if the rotor attains synchronous speed, the secondary rotor EMF would vanish. So it can never attain the synchronous speed. Now, for the current value for the secondary will be say E2 dashed is equal to SE1 is impressed upon the short-circuited rotor, and rotor impedance is per phase is R2 dashed and X2 dashed as standstill. So corresponding to a frequency SF or slip frequency, it will be R2 dashed and SX2 dashed. So the current will be now Z2S is root over of R2 dash square plus S square X2 dash X2 square, or Z2 dash, that is the effort quantity, will be R2 dash square plus S square X2 dash square. So the current in the rotor circuit will be rotor EMF divided by the rotor impedance. So this will be the current. That is the short-circuited circuit. So the current will lag E2 dashed by this angle phi 2, which is tan inverse of Sx2 dashed by R2 dashed. So from here we can draw the phasor diagram, which looks similar to that of a transformer. That is, phasor is simpler. Again, we start with the flux as the reference. So if this is a flux as the reference, we will, at no load, we will there will be that considering the magnetizing circuit, there will be some magnetizing current IM. Now, when the rotor is carrying a current I2 dashed, the current I1 will be this I2 dashed plus IM, that is I1. This is the rotor secondary primary current. So initially the induced EMF in the stator is in the stator we have supply voltage V1 and the induced EMF minus E1. So plus the drops I1 R1 plus I1 X1 will give you V1. And in the rotor circuit we have the current I2 dashed, and it is a short circuited circuit. So I2 dashed R2 dashed I2 dash SX2 dashed is equal to the SE1, which is induced in the rotor circuit. So let us discontinue today. We will continue from here.